Good evening. I'm Arthur Bienenstock, Stanford's Dean of Research. Tonight, we'll learn about the single longest running research project in Stanford's history, called Gravity Probe B. It was also one of the first multidisciplinary projects at the university, bringing together physicists and engineers who have spent over 40 years developing a way to test Albert Einstein's theory of general relativity. Einstein's theories are the basis of what we use to analyze the cosmos and have formed the context for most of the astronomical physics research undertaken in the world over the past 75 years. But his theories are among the least tested areas of science due to the difficulty of performing the tests. In the early 1960s, Stanford faculty members Leonard Schiff, Bill Fairbank, and Bob Cannon speculated that it would be possible to test Einstein's theory of general relativity if a near-perfect gyroscope could be created and flown in a near-perfect space environment. With initial funding from NASA, they hired Professor Everitt in 1962 as the Gravity Probe B's first full-time researcher. The senior NASA spokesman has said that this project was not only the longest-running mission in NASA's history, but it was the most difficult mission it had ever attempted. Last year, NASA, in acknowledging the extraordinary success of the Gravity Probe B project to date, awarded Professor Everitt the NASA Distinguished Public Service Medal, which is the highest NASA honor given to a person outside the US government. Since the beginning of this project, more than 72 PhDs, 15 master's degrees, and 5 engineering degrees have been earned by Stanford students through their work on this project. In the course of this research, many new technologies have been invented that are contributing to other branches of science and engineering. One example is a revolutionary system to improve electronic detectors developed by the project that has enabled digital cameras to be faster, more efficient, and more durable. Another example involves the advances to the global positioning system that are now used both for landing airplanes and for farming. The GPS system developed by the GPB group is now on John Deere tractors throughout the world to help farmers plow and plant the straightest rows of crops possible, even on the most uneven terrain. To tell us about this fascinating program is the project's leader, Professor Francis Everitt. Professor Everitt was born and educated in England. He earned his PhD in physics under the tutelage of Nobel laureate P.M.S. Blackett. He then went to the University of Pennsylvania, where he worked for 2 years before Bill Fairbank talked him into coming to Stanford to work on GPB in 1962. Francis has a wide range of interests and expertise. He's generally acknowledged as being the foremost authority on physicist James Maxwell, upon whose work Einstein built his theories. He is an avid skier and has run the San Francisco Marathon 3 times. But he has never used a computer. Never. He does all of his computations either in his head or by hand. Please join me in welcoming tonight's speaker and distinguished professor, Francis Everitt.
Can you hear me adequately? Okay. So we're going to talk about gravity probe B, and this, wait a minute, I pressed the wrong button. That's a good start, isn't it? This is a moment that I didn't see, but other people saw, which is the spacecraft going up into space. We saw it from inside, and this was taken off the coast just south of Vandenberg Air Force Base. So what is gravity probe B? Well, it involves gyroscope, so let us though ask a little bit what we're trying to measure. Whoops, eventually we'll get this thing. Okay. What Leonard Schiff calculated back in 1960, and some of this was already known beforehand, was that if you made a perfect gyroscope, this perfect spinning body, pointing at a star, orbited around the Earth like that, there would actually be two effects of Einstein's general relativity which would affect this gyroscope, cause changes in the direction of spin of the gyroscope. One of them is known as the geodetic effect, and it's because of the motion of the gyroscope through the curved space-time around the Earth. And the other is called the frame dragging effect, which is as the Earth rotates, it drags space and time around with it. Now, this business of curved space-time to many of us seems a little mystical, and I would like to try and demystify it a bit, because, you know, there are surprising things in physics, but we shouldn't be mystical in the wrong way about them, or surprised in the wrong way. And so I'm going to talk to you first about the geodetic effect, and this is an observation I owe to Kip Thorne. It's the one I call the problem of the missing inch. So what does that mean? You'll see in a minute what this means, but imagine drawing a circle 4,000 miles radius in space, empty space. And you would find that the circumference of this circle is 2 pi times the radius. Now imagine your atlas picking up the Earth and sliding it inside that circle. If you could still measure the radius, and if you could still measure the circumference would be a little bit less than 2 pi times the radius. How much less? 1.1 inches. And this has the effect that it changes the direction of spin of a gyroscope, and you can see this quite easily here. Here is the missing inch, which is a bit more than a missing inch. Now we're going to put them together, and as you go around, you can see the direction of spin of the gyroscope will gradually change. And we're hoping to measure this to maybe a part in 10 to the fourth, possibly a little better than that. So you can say, if you like, indirectly we're measuring this missing inch to 1/10,000th of an inch by means of the gyroscopes of gravity probe B. And that's the first of these two effects that gravity probe B measures. The second, Leonard Schiff gave us a very interesting analogy, and a valid analogy, even one that's better than you might at first think. Imagine the Earth is immersed in honey. Then you can picture that as the Earth rotates, it will pull the honey around with it. And if you're a gyroscope floating in midair at the North Pole, it will be dragged around too. And that analogy works actually quite well in a mathematical sense. And that's why people call this the frame dragging effect. You know, so I won't go more into detail, but that's just the second of the effects that, whoops, still getting this wrong. I was meaning to press the pointer, and instead I pressed the other thing. So there we are. And Bill Fairbank used to say this is the simplest possible experiment you could do, not the most complicated. What is it? All it is a star and a spinning sphere and a telescope to connect the two. What could be simpler than that? And there you are, that is gravity probe B. This is what a gyroscope looks like. It's a sphere mounted inside a housing, which we're going to look at in a little bit later. Right here you see one of the things I wish to talk about. Of course, the orbit around the Earth isn't quite a perfectly circular orbit, and the first man who worked this out correctly was Daniel Wilkins from the physics department, a graduate student, and then John Breakwell from the Aero-Astro department developed a new way of working it out that was much simpler than Wilkins. And any of you who knew Breakwell, he was a really interesting man. The calculations we originally did was about 30 pages, and Breakwell looked at this and said, came back the next day with the whole thing worked out in 3 pages in a very elegant way, using a method that had been devised by Laplace in 1789. Physicists forget these things, which engineers know. Okay, well, there we are. Now let's look a little bit beyond this. NASA has done other things to test general relativity besides Gravity Probe B, putting laser reflectors on the moon. You sometimes wonder, okay, Gravity Probe B, was there a Gravity Probe A? Yes, there was, launched in 1976. It consisted in making a very accurate hydrogen maser clock, putting it in an orbit that went into a rocket that went up to 10,000 kilometers, and seeing that the clock went at a slightly different rate at 10,000 kilometers above the surface of the Earth than on the ground. And then there's also radar time delay. But here is your first picture of what the Gravity Probe B spacecraft looks like, and that is a human being. Okay, now I'm going to tell you 7 interfolding stories. So let's look at these stories. We're testing Einstein, that's fine. To do this, we have to develop some unexpected technologies. It involves 2 Stanford University departments. Actually, we've had students from 11 departments in total on it. There have been not 72, 79 PhDs at Stanford and 13 at other universities. We've had a total of 353 undergraduates working with us. Interestingly enough, high school students have also worked with us quite successfully. I think the count is around 55. Artie Binstock's already mentioned some interesting spin-offs. I will talk maybe about these a little more. It's been a definite symbiosis between NASA, ourselves at Stanford University, industry, especially Lockheed Martin, but also some very other important industry involvement. And let's look at this last bullet. In the process of getting an experiment going, eventually you reach the point where you go and talk to the NASA administrator. This is a very orchestrated thing, you know, where people at NASA headquarters are talking to you, and then they eventually take it up to Mr. Beggs, who was the NASA administrator at that time. And it was nice, very nice presentation, somewhat orchestrated and choreographed in advance, and everything had really been decided already it would go ahead. And anyway, nice talk, and then Mr. Beggs made 2 remarks that I remember. So one of them was, okay, when this finally flies, don't forget to thank NASA for it, because a number of scientists do tend to talk about how wonderful they are and forget to thank that NASA played a small part in it. So I'm glad to do that. And then he said, this is going to be a very interesting experiment. And everybody said, yes, well, I mean, testing Einstein, that's very interesting. Definitely very important. And Mr. Beggs said, no, that's not what I meant. We are delegating responsibility to managing this to Stanford University. This is going to be a major program, and you are going to be the prime contractor on this. It's going to be a very interesting experiment to see whether we can really pull this off. A lot of thought had gone in prior to that this would have to be organized this way. So what Mr. Beggs, mean is it's going to be a very interesting management experiment. And so that's what it has indeed been. Here are some of our key people. Brad Parkinson was a co-principal investigator. John Tanur, Dan DeBray, and here we have two people, Brad and Dan from the Aeroastro department, John Tenor from the physics department. There are a number of co-investigators, Sasha Bookman, Matt Kaiser, John Leeper, Jim Lockhart. Jim is at San Francisco State University, Barry Milfelder and Mike Tabor. All of these people are some of the key leadership of the experiment. So we'll talk about these 7 stories. I say they're interfolded because I won't be talking first about one and then about the next, but sort of you will see them coming up, these themes, as we go on. Here is the great moment of launch, and it's a really awe-inspiring, inspiring experience. That, by the way, this is at Vandenberg Air Force Base, is a tower which is 30% higher than the Leaning Tower of Pisa, mounted on a railroad track, and that tower normally is around the launch vehicle, and you get the launch vehicle, the actual payload assembled in it on the top at the end. The clamshells are going on to close it off. There you see them after closed off. And then at 3 o'clock in the morning before the launch, this is withdrawn. And then there's that tremendous moment of roaring and launch, and then we go up and then saying farewell to it, almost the last sight. This was 45 minutes later, actually seen from the first ground pass over Norway, and it's a great moment because you can see that the solar paddles have unfolded. And it was a huge cheer when we saw that, because there have been spacecraft in which the mechanism didn't work and then you have a nightmare. So great relief that was. Whoops. This is waiting for the launch, waiting for the moment. Brad Parkinson, you've seen Rex Jeverdon of NASA, other people from NASA, and Rob Brumley there. And this is the moment afterwards with the director of Marshall Center, Dave King. But what does this say? Boeing and luck. We got about a perfect orbit, and it's good to have luck as well as Boeing on your side. What does this mean? Well, we need to get into a very exactly polar orbit, and the 3 sigma insertion accuracy for this particular spacecraft is in that whole square. We needed to be within a limited range within the square. We needed to be within this lozenge shape. If you were in there, we would be okay. So we were thinking we would have to tune ourselves from somewhere over there into this, and bingo, we landed right up in the exact middle. We couldn't have had a more perfect orbit. And there was a 1-second launch window. If we'd missed this by 1 second, it would have had to wait till the next day. So what this then in turn means is that somebody pressed the button to within better than 0.3 of a second to land us exactly there. And of course we weren't to know that, and it was luck. But luck's a good thing to have. Okay, now where do we go from here? So what's a gyroscope look like? You can actually come down afterwards and look at it. It's a sphere the size of a ping pong ball, which is 1.5 inches. And this sphere is coated with metal. Here is the sphere. It's placed inside a housing where it's electrically suspended. We'll look at all of this later. There's another picture of it. The sphere is supported electrically. It's spun up to begin with by means of gas. It's read out magnetically, and it runs at low temperatures, cryogenic operations, a few degrees above the absolute zero. So now let's talk a little bit about gyroscopes. What you see here is electrically suspended gyroscopes of this general type running on the ground. How well do they work? These numbers are actually ones that I have to guess because they're classified, but I can make the same kind of calculations that the Chinese can make. And so the performance turns out to be about 10 to the minus 5 degrees per hour after you've modeled them. Laser gyros are not really quite so good. They tend to be about 10 to the minus 3 degrees per hour. How well do we need to do gravity probe B at the sort of accuracies I was talking about? Somewhere about 10 to the minus 12 degrees per hour. So that's quite a thought. Let me give you another thought. We're hoping to measure these somewhere down to 1/10 of a milliarc second. That's 1/10 of 1,000th of 1/32nd, or 3600th of a degree, which turns out to be this 3.2. Has this stopped working? No. 3.2 times 10 to the minus 12 degrees per hour. That's the width of one of your hairs seen 100 miles away. So that's a small angle. Artie's mentioned Leonard Schiff, Bill Fairbank, and Bob Cannon. And now I want to just give you a little philosophy. There are perhaps two ways, in broad ways, in which you can do physics. One of them is you can try and make the effects you're looking at much bigger. So if you think about SLAC, we have a 2-mile long accelerator to make objects go faster and faster. Maybe you'd like one 100 miles longer, you know, and so forth. I venture to call that near infinite physics, where you're trying to make a huge effect. We don't have that possibility here. What we have to do is not to make the effects big, because we can't change them, but the disturbance is small. So this is near zero experiments versus near infinite physics. And it turns out for gravity probe B, we have to develop 7 near zeros just for the gyroscope. We have to make a very homogeneous sphere. We have to do something I'll call drag-free, a very round sphere, very low magnetic fields, very low pressure, very low electric charge, very low electric dipole moment. And we'll talk a little bit about these as we go along. But this two classes of experiment have a very interesting and long history. I think the first really serious near zero experiment was done by Henry Cavendish back in the year 1798. And reading Cavendish's experiment even today is an education. Okay, we suspend these gyroscopes electrically. So here it is being suspended, and we put voltages on it. Now, some quite interesting numbers here. You see, you have to be able to suspend it on the ground to test it. You have to be able to suspend it at very low acceleration in space to make it work effectively. That means it has to be suspendable over a range of 9 orders of magnitude. Let me talk the near zero story in a slightly different way. To support this gyroscope on the Earth with a 1,000th of an inch gap between the housing and the sphere, you need 700 volts. Up in space, we were running at 0.2 of a volt. That's 3,500. The disturbances that act, because it's not quite spherical, even though we've made it incredibly spherical, goes the square of the voltage. So 3,500 squared is 12.5 million. And this means that you ought to be able to make a gyroscope that's 12 million times better in space than on the ground. You haven't yet made it, but what it means is that it's not crazy to think about it. So this was developed by a group headed by Bill Benzie, and it was a whole remarkable suspension system to do this. We have to have it centered in the cavity during science. We have to spin it up, which means switching it to a higher voltage. And we have to be able to offset it in certain places. We have to have various other things, and we finally have to use it. And here's the names of just a few of the people who've worked on it. And I throw about things we call nanometers, and you'll see more about nanometers. Well, the thickness of a sheet of paper is 100,000 nanometers, and the diameter of an atom is about half a nanometer. So these are things that we're going to be talking about with respect to this suspension system. Okay, now we're going to have to spin this gyroscope up. If you think about it, this is actually going to rapidly see to be a much trickier problem than you would have imagined. Why? Okay, what are you trying to do, make a gyroscope? You're trying to make a gyroscope totally free of all disturbances, a spinning sphere with nothing disturbing it. But what do you do when you spin it up? You have to put forces on it, or torques, to spin it up. So there are actually three problems I'd like to quickly allude you to. The first is what I call the torque switching ratio. This is a calculation, a physics calculation you can do in 2 lines. And what it tells you is that if you're going to spin it up, you have to put a certain force or torque on it. And then you have to switch it off. So how much do you have to switch it off? Well, you have to be the performance you're trying to finally reach, this 1/10,000th of an arc second per year, times the time it takes to spin it up. That's 14 orders of magnitude. Would you like to know what 14 orders of magnitude are? If you reckon Bill Gates' net worth in pennies and multiply it by 20, that is 14 orders of magnitude. I had figured out the way to do this with the help of Baganoff. We went away and wrote up the paper, you know, and finally we got to the end. That was 16 days. By the way, Bill Fairbank was a man that if you wanted to get on with work, you had to hide from, so we went and hid and just worked on this paper for 16 days. Eventually got it out, and then Dan said to me, or I said to Dan, oh, how difficult it is to get the gas out of this whole system. And we did a calculation and got the shock of our life, because we needed a pipe 6 inches in diameter to get the gas out of the system. If I had known a little more, I would have known what this locomotive engineer G.J. Churchward said in 1895 about steam engines, that any fool can get the steam into the cylinders, but it takes a clever man to get it out again afterwards. Why is this? Because you're putting the steam in at high pressure, or the gas for spin up at high pressure, but you're taking it out at low pressure. And so you need a much bigger pipe. And we rediscovered something that was known in 1895. Okay, now how is the next interesting question? How do you measure the direction of spin of a perfectly round, perfectly uniform sphere with no marks on it? And this is one of the places where superconductivity comes in. So here is the sphere, and it's coated with a superconducting metal, which is one of the reasons, but by no means the only reason for running at low temperatures. And it turns out when you spin a superconductor, it gets a magnetic moment aligned with its instantaneous spin axis. So you get a pointer in the spool just because it's spinning. By the way, if you stopped it spinning, it would disappear, and if you spun it in the opposite direction, it would point in the other way. So that's the basic idea, and it sounds nice and simple. Actually, to get it to work took enormous work by Jim Lockhart and Barry Mulfelder, and then other people, including support from Terry McGuinness at Lockheed, and this was a tremendous effort and a great moment when we finally showed that we would be able to not have any signals coming in other than the one we were interested in. And it all goes into a superconducting box there, and here is the great moment, actually done in ground-based testing, where we discovered that for all 4 gyroscopes we were going to beat the requirement. Notice this little thing here, centering stability 50 nanometers. You remember I defined what a nanometer is, and also some of the shielding that's required. Okay. Now, how does this all go together? Well, we don't have 1 gyroscope, we have 4. And obviously I said you need a telescope, so we have a chunk of quartz, fused quartz, that's glass, with a telescope and a block of quartz there and some gyroscopes. and it all goes down to get together, and all is very stable at low temperatures. I like this quotation from H.A. Rowland around 1900. If you want to make a really precision experiment, design a precision apparatus as if it were made of jello. And if you know how to design it made of jello that it'll still be stable, then maybe it'll work. And fortunately, our jello is at low temperatures, 3 degrees above the absolute zero, 2.5 degrees above the absolute zero, which stabilizes it more. It's also in space so that it doesn't sag under its own weight. I've made a number of telephone calls in my life. It's arguable that the most important telephone call I ever made was to this gentleman, Don Davidson, whose name had been given to me, who's a master of fabricating quartz. He's still alive, he's 94 now, but I stay regularly in touch with Don Davidson. Here you see him hands-on with that quartz block, down at a company called Speedring, as it was, but he goes down there, although he didn't work for this company, and he had played an enormous part in developing how you manufacture the gyroscopes and how you manufacture the telescope, and we'll talk about this. And here's the thing coming together, Dora and Bardis. And then this all goes into a structure which is about 10 feet long there, which is going to go down into a thermos bottle. Here it is over at Lockheed Martin Assembly, trying to ship to Stanford. Here are the names of just a few of the team. Dick Parmalee. I figured chose to put in one name of a technician, Mark Molina, who played a very critical part in this experiment at a certain point. I could put in many other names, and I will, but I wanted to put this name in. You know, every space program gets into trouble at some point. And the question is finding people who get you out of trouble. And those may be high-level people, or they may be not so high-level people. We got into very interesting trouble where on our third device, putting it together didn't quite work. And John Tanua, whom I showed you the face of earlier, I went into his office and he said, the calmest man you ever met. His face was white. This was because something that should have been running at 24 degrees above absolute zero was running at 100. Inside a piece of apparatus that had taken 2 years to assemble and would take 2 years to rebuild. When you are spending $1 million a week, that's a serious question. If you can, which is partly through Bill Reeve leadership and others, cut that, as we did, to 8 months, it's still agonizing, but we survived. And we wouldn't have survived if we had had to go to the rebuilding. Mark Molina did a lot of practices on the repair job. I won't describe what the repair job was. Went to about 30 different machine shops up and down the Bay Area, talking to them, how will I do this? Figured out how to do it, and it worked perfectly. So, you know, there are many heroes in a mission like this. And there's the big thermos bottle containing 2,300 liters of liquid helium, under test on the Stanford campus, having been shipped over from Lockheed. Finally, it gets completed, all the testing. This, by the way, is an interesting moment when you see your $300 million baby swinging from a piece of string. One of the things we had to invent, and it was this graduate student, Peter Selzer, invented, was a device for controlling the helium in space. It was then further developed, engineered for space by people at Marshall Center and elsewhere. This was what made possible the NASA RS mission, the NASA COBE mission, the WMAP mission, this little invention of Peter Selzer. and it's a porous plug device, which I may tell you a little bit about more later. Now, this is the only equations I'm going to show you other than the basic shift one, and you don't need to follow the equations. Let me make the point. Supposing we have made an absolutely perfectly round sphere. Regrettably, it isn't made quite of perfectly uniform material. So you're going to support it about its center, but accelerations will act through its center of mass, which might be a millionth or half a millionth of an inch away. Very small distance. What does this mean? This is high school physics equations up there you can put in as what it means, and you finally get a little formula which says the accelerations times the delta r over r has to be less than the peripheral velocity of the ball by the performance you're trying to get. So you plug in the numbers, and you ask yourself, how uniform a sphere would I have to make to operate on the ground? It would have to be uniform to 6 parts in 10 to the 18th. And let me assure you that's utterly ridiculous. What would happen in an ordinary standard satellite? You have accelerations of the order of 10 to the minus 8g. Then it would only have to be uniform to about 6 parts in 10 to the 10th. And we don't really, I think, have any materials that good, but it's not quite ridiculous. But finally, if you make the spacecraft drag-free, you can find yourself with a gyroscope that only has to be uniform to a few parts in a million, and that we know how to do and have done better than that. So I will have to tell you about drag-free as we go on, but basically what you do is you sense the position of the gyroscope and blow out gas to make the spacecraft chase after the gyroscope, and you can reduce the accelerations. We'll be seeing about that. So these are my first 2 near zeros, right? First and second. It has to be drag-free and it has to be very spherical, very homogeneous. So how do you make the spheres? This was developed initially at NASA Marshall Center. It's a very interesting combination of high-tech and low-tech. These are sewing machine motors, so that's why it's called relatively low-tech. But here's the lapping system that was used, invented by this gentleman, Wilhelm Angela, and then after a while, these people keenly working on it at Marshall Center. Incidentally, the best one ever made at Marshall Center was made by a 17-year-old high school girl who perhaps had more patience from this exciting summer job that she had. I wish I had remembered her name. I sometimes wonder if she might be a grandmother by now, but anyway. Whatever. We've likewise had further developments when it was transferred to Stanford, and so there's names up there. I'm glad to see Frani Masalia is with us tonight. Okay, of course, not only do you have to make it, you have to measure it and see how good it is. And let's talk about that. The roundness measuring machine that we used was a very fancy dial indicator device, and you might be surprised, but that's still the best way of measuring roundness, which is able to measure to 1 nanometer. You remember 100,000 nanometers is a sheet of paper. And here it is measured. If you were to blow this up to the size of the Earth, the highest mountain would be 5 feet, and the deepest ocean would be 5 feet deep. And developing that, some of the mapping techniques and all of this was a bunch of interesting students whose names you will find there. By the way, let me tell you something. Whenever a physicist shows you something and he calls it typical data, this always means the very best piece of data he ever got. So with that definition, this is a typical sphere. I mentioned we needed very low magnetic field. The technology for this was invented by Blas Cabrera with Bill Hamilton supported. It's very strange technology. It consists in taking a lead bag which is folded up, pushing a plunger down into it and expanding it, and that gets you a lower magnetic field than you started with. And you actually do this 3 or 4 times with successive lead bags. And we got lead bags with 10 to the minus 7 Gauss, that's 1/10,000,000th of the Earth's field. And with the complicated shielding devices that were developed by Blas and then Jim Lockhart and others, we managed to get 10 to the minus 12 attenuation of the AC shielding, which means we really got very isolated things. For those of you who think in terms of decibels, that's 240 decibels of shielding. It's quite remarkable. John Mester played an important part in that also. Here, by the way, is that porous plug device I referred to, and here's some of the spin-offs, and here's the students at Stanford. I won't go into the details there, but you can see some of the names and some of the things that came out of this. Okay. The payload was built at Lockheed, or the Dewar, the thermos bottle, and was then brought over to Stanford, tested at Stanford, sent back to Lockheed, and then the spacecraft ran around it. Here are some of the key people. The main program manager was Hugh Dougherty. He was succeeded by Bill Reeve, who had played a lot of part. Norm Bennett was the head of the software development. Bob Schultz was the systems engineer, both for Stanford and Lockheed. That was a very happy collaboration. And this is the moment when it's packed up, ready to go down to Vandenberg Air Force Base. It took 7 or 9 hours, I can't remember which, driving down to Vandenberg Air Force Base with police outriders all the way, and quite a dramatic experience. So there we were, and this was a moment of parting of considerable emotion. And now suddenly you're up in space and you're in a completely new world. And this, on the Stanford campus, is the Mission Operations Center, a mixture of Lockheed people and Stanford people and Ames people and Marshall Center people. And Marcy Smith was from NASA Ames, was the key person in this. Gaylord Green was the program manager during this phase of the experiment. And here is something we call the anomaly room. So let me talk to you a little bit about this very quickly. I don't want to go on too long. But there are people who know how to run spacecraft. And there are physicists who don't have a clue, but who do know about the instrument, physicists and engineers. And somehow or other, you've got to bring these teams together. And you have to bring them together while you're still building the spacecraft. I think we would have had incredible difficulty if we hadn't been able to do this on the Stanford campus. Many of the people actually came down from Berkeley, where there had been a previous satellite that reached the end of life, but Marcy came over from Ames, and there was about a 2-year training period. Looking at it from sort of my distance, the best analogy I can give to you is it's rather like theater. What do I mean by that? We went through rehearsal after rehearsal. We had, I think, 10 rehearsals of what it would be like to launch and run the spacecraft, including putting in anomalies where problems take place and how do you recover from this. And this was where the people who knew how to run the spacecraft taught the physicists, and the physicists taught them. I say it's like theater, but it's like theater in another way. It has to be scripted, because when you've got the mission director and you say, well, I think something is wrong here, but I don't, maybe we're not reading the right signal here. That's not good enough. You've got to give an exact statement. You've got to have an agreed language, just as in landing an airplane, there's an agreed language between the controllers and the pilots and so forth. So all of that went through many rehearsals, very interesting process, where I was just an awed onlooker. Okay, now you get to the point where, fine, you're up in space, but you get an anomaly. The spacecraft mysteriously points off in some strange direction. What do? There are two things you've got to do. You've got to keep the spacecraft alive, and you've got to figure out what to do. And a physical separation where you have the Mission Operations Center and also an anomaly room. By the way, there wasn't much of an anomaly here, because when there was a real anomaly, you would have 20 people in this room discussing what to do, while the people who are running the spacecraft are staying over there, keeping it alive, maybe in some safe mode. And then finally, when you've figured out what to do, maybe you run some things through an integrated test facility at Lockheed, and finally you know what to load up to fix it. Fascinating process, and it went very well with lots of scares along the way. Okay, so here for the first time we levitate the gyroscope on space. Switch on the volts. Initially it's over here. That's 30 micrometers. 30 micrometers is just over 1/1000th of an inch. And you see we switch it on and it jumps to the center. Run it for 6 seconds and switch off the suspension. And lo, it goes in an elliptical arc and then bounces. Why does it bounce to a different position? Because the spacecraft has moved a little bit in that time of the bounce. And here are the 3 directions. So that's the first item, and the names of a few people involved with this suspension operation. Now we're a little bit better off because we are now seriously suspended at the final low voltages. Do you remember that I mentioned that we had to have a centering requirement from the gyro readout, which was 50 nanometers? In fact, the suspension system is so stable that it remains stable to about 0.5 nanometer, 0.45 nanometers, and this is the noise floor on that. Look up here though, do you notice that there is this is measuring the accelerations on one of the gyroscopes. A couple of things, there's some frequencies here. Why is this? The spacecraft is rolling about the line of sight to the star relatively slowly at this point, about 10-minute period. The gyroscope is not quite at the center of mass of the spacecraft. This is twice the orbital period in there. This is because it's not yet drag-free. Okay, so the suspension is working on orbit, and that's nice. Now, how about the gyro readout? We read out by means of this London Moment device, and here we are on orbit. Sometimes things work just a tiny bit better on orbit than in ground-based testing. Here is the performance requirement and the noise performance. And you see on one of the gyroscopes, which is gyroscope number 2, we actually are quieter. The noise at the roll frequency of the spacecraft is less than the requirement. For another one, it's not quite so good, gyroscope number 2, but they all either met the requirement for this. And here is measuring the angle of the gyroscope. Peak to peak of that is 24 arc seconds. And now we are rolling at our final roll rate, which was a 77.5 second roll period. So the spacecraft is rolling relatively slowly about the line of sight to the star, just over a minute period. Fine, so there we are. Names of people up there again from Stanford and Lockheed. One of the interesting things is that we sometimes find things which we made estimates before the ground are a little bit better than we expected. This is how well balanced the gyroscope is, and we were expecting 18 nanometers for the mass unbalance. Mass unbalance is that distance between center of geometry and center of mass. In fact, for the 4 gyroscopes, these are the numbers that finally came out from some very interesting tests that we could do in space but not on the ground. And this is another related effect. Okay, drag-free and drag control. What we use is rather interesting. We use the gas that boils off from the helium vessel. The helium vessel stayed cold for 17 months and 9 days, a little better than we were actually aiming for. And this gas boils off, and we run it out through a thruster, and we use this to point the spacecraft at the guide star and also to compensate the drag. And the first student who worked on that was John Bull, and then there were other students, and then the final work was done at Lockheed to engineer it for space. So you remember I said that you get an acceleration on the gyroscope at twice the orbital period when the drag-free system isn't switched on. Now look here, we switched it on, and suddenly that acceleration is cancelled. The spacecraft is following now that accelerometer. This is the acceleration parallel to the line of sight to the star. The more important one, slightly more difficult to grasp, is the cross-axis acceleration. Our gyro spin directions are pointing to that. And here we have the roll rate of the spacecraft, and here we have that gravity gradient. And the cross-track average acceleration is 10 to the minus 11 g. That's a factor of 1,000 less than the natural acceleration on the spacecraft, roughly speaking. So it's a pretty good compensation. It makes the gyroscopes work very substantially better. Okay, now one of the near zeros that I talked about was we have to be at extremely low pressure. And this is a very interesting item. You see, when you want to get very ultra-high vacuum, as standard procedure, you bake your system out. Fine. Well, we are doing a very horrible thing. We may have a perfectly baked out system, and then we blow gas in it to spin it up, which is absolute no-no. You mustn't do that. And I think it was John Leeper and then John Tanua developed it, who understood what to do with this. You have to bake it out. But baking out when you're in the low temperature world means something very different from when the normal world. It means raising the temperature from about 2.5 degrees above absolute zero to 6 degrees above absolute zero. And we did that. It was an exciting and actually slightly scary moment on Earth. Now, before bake out, the characteristic spin down time which you could measure was 50 years. After bake out, these gyroscopes, the gas had so much gone that it was characteristic spin down time was 50, to go to half the spin speed was 15,000 to 25,000 years. By the way, when Senator Stevens came on a tour, I quoted these numbers, and he said, does this mean it's going to be, I have to wait 25,000 years to know the results of Gravity Probe B? So we reassured him about that. It shows we got especially low pressures. By the way, one of the things you do is need to ask yourself serious questions. Why are these spin speeds not quite the same? Because if you're all at the same pressure, you would expect the spin down rates to be the same. And there's a significant effect there that one has to eventually worry about, that they're not quite the same. Mentioned about electric charge. We actually have a technique for discharging the ball on space. It charges up at about 1/10 of a millivolt per day, and we need to keep it to very low voltages. And here you see a very clever device developed by Sascha Buchmann for discharging the rotor. So those are 6 of our 7 near zeros, and I haven't talked about the 7th, which has actually been the trickiest one, but I can talk about that if somebody wants to ask me a question. But a telescope, we need a telescope, and so I've said nothing about the telescope. So here's the telescope, and here's this marvelous man, Don Davidson, and it was about the telescope I first discussed with him. This is a telescope, all made of glass, 150-inch focal length. Physical length is just over a foot, 5.5-inch aperture, and we have to get the star image, which is about 1,000 times bigger than what we're trying to measure, very accurately measured. And in order to do this, you have to somehow divide the star image. Your idea might be, let's have a pyramid and let the star fall on it, and then you've got 4 signals coming out and compare the intensities. It took Don Davidson 2 years to figure out how to do this, and this is how it gets done. We have a beam splitter, so we form 2 star images, and then you allow the star image to fall on a very sharp prism. We call it a roof prism. It's shaped like the roof of a house. That prism has no chips on it greater than 1/1,000,000 of an inch, and we now can then, as the star moves back and forth, compare the intensities. Got a very beautiful star tracker. Took Don 2 years to figure out how to make this prism with no chips on it, and when he thought of the idea, it was so obvious, why didn't you think of it sooner, you know? And here again it is, and here it is under test, different ways. You can see some of the details of it. There are the detectors. Here are some of the people who worked on it at Stanford, and so we go on. We have to find the guide star because each orbit, for half of the orbit you're blinded and can't see it, and then you have to reacquire it. And this shows the reacquiring process. And by the way, the whole business of acquiring the guide star caused John Kirschenbaum's hair to get a little bit grayer in the first 30 days of the launch of GPB from Lockheed. We were very fortunate, in addition, to get Lou Herman to come in with some additional advice. And finally, it works very successfully, points well, and we can subtract this gyroscope signal from the telescope signal from the gyroscope signal and get our data. And then we have to worry about the star. Supposing we're doing a relativity measurement, but unfortunately your star is drifting around in the sky. And Erwin Shapiro figured out the way to do this, to find a guide star which is both a visible star and a radio star, which just happens to have a very remote quasar nearby. And so the star we picked on, after a long story, was IM Pegasus, which is both a visible and a radio star. And then with a very large array, what's called very long baseline interferometry, you can measure its motions very accurately by radio methods and then have it. Interesting question, are we pointing at the right star? Greg Henry of the University of Tennessee was making simultaneous measurements by an optical ground-based telescope. You see they fit perfectly, so we really do know we're pointing at the right star. And the thing that annoyed you at first, that the star is a variable one, turns out to be a useful check, which is an example of a principle of Bill Fairbanks that I'll tell you about maybe. We're almost at the end of this. Let's just go on and show you a couple more things. When you talk about somebody dithering about, that's not usually thought to be a good thing. And when you talk about aberration, none of us are supposed to be aberrant, but dithering and aberration are actually essential to Gravity Probe B. So what does dithering means? It means the following. We're measuring angles, right? No, we're not measuring angles. We're measuring volts, which you want to convert to angles. And you're going to point at a star with a telescope, but you can't point perfectly. So you have to subtract the telescope signal from the gyroscope signal. Would it not be annoying if the gyroscope is reading 1 volt per arc second and the telescope is reading half a volt per arc second? You have to fix that. So the concept of dither is you put an oscillatory signal into the pointing deliberately and then make sure that these both come to the same amplitude. And when you've done that by adjusting the telescope to fit the gyroscope, you're fine. And you can make an honest subtraction. But we still don't know whether our volts are really arc seconds. And this is where something that Bill Fairbank used to call the anti-Murphy law comes into play. Murphy's law is that everything will go wrong. The anti-Murphy law is that when you finally understand what you're doing, to your surprise, things will go right. And it turns out that nature is very, very kind, because nature injects into Gravity Probe B a calibrating signal, the aberration of starlight. This was discovered by Bradley in the year 1729. What he found was that as the Earth goes around the sun, and you point a telescope out, of course, at a certain point, you're going transversely across the line of sight to the telescope, and during the time the light comes into the telescope and then reaches the detector at the end, the telescope's moved over, and it's moved over by an amount that you can know very exactly, the aberration, and this is 20.4958 arc seconds at a 1-year period. And also, as we go in orbit around the Earth, there's a calibration too from this aberration, and it all works out nicely, injecting a calibrating signal. Nature is your friend when you understand, and it took us a little time to understand this. Okay, we're coming to the end now. So there were 3 phases: the initial checkout, the science phase, which lasted 353 days, and then we did some post-experiment tests, which actually lasted 46 days. Lockheed gave us a bonus of 23 days on the lifetime of the duo, which was quite nice. And what you're doing here is, during this post-experiment phase, a principle that I know first defined by Cavendish: if you've got a possible error in an experiment and you don't know how bad it is, what you ought to do is not to try and make it less, but trying to make it worse by some known amount and calibrate it. And this is the things that we did during this phase. We've invented ourselves a little mantra for Gravity Probe B, and it's this: always be suspicious of the news you want to hear. It's a very good discipline, and I've been surprised how often, whether it deals with scientific effects or budgets, that you always want to hear the good news, but you sometimes need to be more watchful. Here is the data analysis team headed by Mac Kaiser, and Joe Jack of Marshall Center, the rest are Stanford people, and the large supporting group around here, including a nice bunch of students. We've had 9 students working on this data analysis, and we should be ready by April of next year with the answer. I would like to say a word about the NASA Marshall Center Stanford collaboration. During the first phase, it was a matter of technology development and studies and an in-house phase B study. I want to pay great tribute to this man, Dick Potter, who died last year. You know, whenever you work with another organization, the first thing you've got to do is to find somebody in that organization you can trust. Trust means they will not necessarily tell you what you want to hear, but will tell you what you need to know. And Dick Potter was very good at this and very helpful. At a time when we had a budget of $180,000 a year, you know, so we weren't an important Marshall Center program. But he got us off on the right foot with Marshall Center. I'd love to talk about this subject, but I think I will pass over it, though it's all a very interesting subject, much of which I learned from Brad Parkinson. Here's the different managers, Rex Jeverton and our current manager, Tony Lyons. There's been a most interesting report, the Calder-Jones report, on Gravity Probe B as a management process. I won't quote from that, but I would like to quote a casual remark that Brad Parkinson made to me in 1985. What we're doing here is a cross between an academic program and a Silicon Valley startup. And that's what Gravity Probe B was being. So a lot of things we had to learn in that. And this isn't by no means a complete picture of the Lockheed and Stanford team, but you see some of the names and some of the people. Where do we go from now onward to a new program, the STEP program? But I think I will not talk about the STEP program unless somebody wants me to do, and I will stop at this point.
I'm sure Professor Everitt will answer questions, but you're really going to have to wave because we can't, the bright lights make it hard for us to see you. I see a hand up there. Is there someone with a microphone?
It's okay, I can speak well enough, I believe.
Good.
I'm very curious as to the method of discharging the broacher. Were you able to do that with ionized gas as a non-contact method?
Ultraviolet light.
Bravo. Brilliant.
Yes.
Before you go to the first slide, I have a question about the geodesic precession.
Mm-hmm.
It seemed like the extra angle was in the direction of the orbit.
Mm-hmm.
I guess I'm trying to understand that. So, I mean, because when the probe's going around the Earth, you know, it's in curved space, so it should make a circumference in less than 360 degrees, right?
Mm-hmm.
So
Up there.
If the data gives us the results we're anticipating, how close does that move us towards finding an analogy between matter and graviton, similar to that between charged particles and photons? In other words, a Maxwell equation set for matter and gravitomagnetism.
I'm sorry, I was slightly distracted by the sound back there. I'm not sure that I quite understand the question.
Will this data help us to derive a set of equations that are similar to Maxwell's equations, but for matter and gravity?
Okay, one can, in this approximation, which applies in weak gravitational fields, actually develop a very interesting analogy between Maxwell's equations in electromagnetism and Einstein's equations of general relativity. Another way of looking at the meaning of the frame dragging effect is that it has an analogy to magnetism. So let me explain that. If you have an electrically charged body, we know that it exerts an electrical attraction or repulsion, which goes as the inverse square law, just like gravity. But that's electrostatics. Now, if you have a charged sphere, electrically charged sphere, and spin it, it becomes a magnet. This was actually that same man, Rowland, did the first experiment demonstrating that in the 1870s. So you can look at the frame dragging effect as being, and this can be worked out again mathematically to really work, as being a gravito-magnetic effect. You can get equations, Einstein's equations, reduced to a very similar form to Maxwell's, with factors of 2 here and different signs here. The factor of 2 is because, quotes, the graviton is expected to have a spin of 2, whereas the photon only has a spin of 1. And so in some sense you can say we are checking that. But of course you don't require gravitons to produce this effect. I mean, this isn't a proof that the graviton exists. If we get the same answer as Einstein, you could say it would be a proof that the graviton has a spin of 2, but it hasn't been detecting a graviton. I mean, you're into a whole different area of problems here of the difficulty of quantizing Einstein's theory. Yeah.
Could you give a brief synopsis of STEP and LISA and the future of the Gyroscope lab?
So what is STEP? We remember the story of Galileo dropping two masses from the Leaning Tower of Pisa and they hit the ground at the same time. Actually, we reenacted this in 1994 for Italian television, and it doesn't really work because of air drag unless you do something lucky, which we figured out what to do. Okay. What Newton understood is that this is much more extraordinary because it says that mass appears in Newton's equation F equals ma, and mass appears in Newton's gravitational equation there, and these two masses have some relation to other. The person who really got this right wasn't Galileo, it was Newton. It's really beautiful to read Newton's discussion in his Principia about it. You ought to feel great shock about this. Why are you not all collapsing on the ground with shock when I tell you this? Think why you ought to be shocked. Suppose the force wasn't gravity but was magnetism, and supposing you dropped an iron ball and a glass ball, you absolutely wouldn't expect them to hit the ground at the same time. So what this tells you right away is there's something very funny about gravity. And Newton completely understood this and told you so in his book. And Einstein then extended it, but never explained it. Einstein's last remark on it was, it's an absolutely baffling phenomenon. Now, interestingly, as I say, the first real experiment was not by Galileo, it was by Newton in 1687. People have gradually shown that to parts in 10 to the 12th, this is true. But if you go into space, you can pick up another factor of 10 to the 5th or even 10 to the 6th. And that's what STEP is about. And it turns out to be, you can either say this is a good idea because if you can measure something better, you should always measure it, or you can look at theories. These theories are all a bit flaky, but there's several reasons why interesting things may happen in this range, 10 to the minus 12 to 10 to the minus 18. So there is the STEP system, some of the apparatus we're using, and you will see squid devices and accelerometers and magnetic bearings and the same detector as gravity probe B. And there are the STEP test masses in orbit around the Earth. And, well, will it have some impact on credibility? We'll see when it goes, but that's the synopsis of STEP. I won't talk about a synopsis for LISA. We'll ask Bob Bayer to do that sometime.
Can I ask a question?
Yes?
Do you anticipate launching that in less than 40 years from now?
Yes, I believe it could be launched in 2012, realistically. We will have to have some good help at NASA to make that happen. But the reason why the whole story is different, we put in a proposal which was very correctly rejected in 2002 because the technologies weren't ready. A chunk of the technologies have now been tested by Gravity Probe B in space, and so those are certainly ready. Some technologies have not, but working with Marshall Center, we've defined a good technology development program for the ones that hadn't been tested. And if you look at it right, those technologies will be in good shape about 2 years from now, provided the money continues to flow in the right way, and which we encourage NASA in various ways to help happen. And then it should be a much quicker process to build a spacecraft. So we have learned a lot, and some of the team have learned a great deal in the time, which makes it not unrealistic, but still very hard work. Yes. Okay, would you like to know how to make a prism shaped like that with no chips on it greater than 1/1,000,000th of an inch? Simple. You polish a flat surface, very flat, on a piece of glass. Maybe you make the back shape of it appropriate for what you finally want to do. You then take another one, also polish it flat, put them together in what one calls weak optical contact, which holds them together, but if you know what you're up to, which Don Davidson does or did, you can get them apart again. And then you come across and take a cut at right angles and polish that surface at right angles. And so each corner protects the other. Why on earth didn't he think of it sooner? Yep. Yes. Exactly. But unfortunately, we're trying to measure one effect that is in the plane of the orbit and one effect that is at the right angles to the orbit. If you had a telescope at right angles to the plane to the orbit, you would see the guide star, but you wouldn't measure the relativity effect. There are some interesting other things you can do, actually. You can put it in an inclined orbit, and then the orbit rotates during the course of the year. And John Breakwell and Richard Vassar, whom I also is glad to be here, investigated that. And from a certain conceptual point of view, you can then do an experiment in which in parts of the year you do see the guide star all the time. And you can even persuade yourself that you might get a better result because you're taking more data, but you then find other reasons why it's better to play it safe and be in a strictly polar orbit.
So on a light note, what you're saying is that between Laplace, Rowland, and Bradley, this is really a bit of new wine in an old bottle. And may I ask the privilege, please, that the members who participate in this could stand right now for a round of applause? Those who are present here.
Well, Tony, stand up.
Thank you ever so much.
Yes.
Can you make a brief comment on that 7-0?
Yeah. The 7th zero was the fact that you want to make sure that your sphere doesn't have an electric dipole moment. This is a slightly technical statement, but let me illustrate what I could mean by this. Supposing you were to have two metal caps made of slightly different material, and when you put them together, there will be a little voltage between them. And this will cause an electric dipole moment, which means that it looks not like a point charge, but like two charges. And then if you get a transverse electric field, this will put a torque on the gyroscope. In fact, we found we do have some these things which we call the patch effect, which were a bit larger than we were expecting, and which now has to be treated in the error analysis, and we have it reasonably under control, but it's a difficult thing to explain in detail, and so I passed it up, but it's actually one thing which, if we'd been a tiny bit clever, we might have got to a smaller thing, and we now know what we should have done, but meanwhile we have to do our data analysis, and it's coming out okay.
I understand you had essentially 1 year of hydrogen in which to get
No, that's right. Can somebody remind me, Mac, can you remind me how much data we have? You heard that?
More than a terabyte.
I'll talk to you about taking a long time in the following way, that I'm still on Christmas card terms with Bob Vesseau, the principal investigator of Gravity Probe A. And last Christmas, the card I sent to him, I'm afraid it's going to be another 15 months before we have the data. Got a lot of work to do. Christmas card I got back said, "I'm impressed it took us 4 years." There are actually several questions you've got buried in that one. For example, one of the things we worried about enormously, you do not want to drop one of these gyroscopes. If you drop a gyroscope spinning at the speed of a sports car engine, it'll smash the housing and maybe cause propagating damage through the rest of the system. And so Bill Benzie designed the suspension system so that if an anomalous acceleration hits the spacecraft through a micrometeorite having hit the spacecraft, automatically and instantly it switches up. And this happened on a number of occasions, though probably not from micrometeorites. The other things that happened, which is maybe what you're also referring to, is were there any times in the year where we slewed off and lost our guide star through some large angle, and did this have any effect on the data? Yes. And actually we'd had a PhD student look at this in a very interesting way of what happens if you get an unknown interruption in the data which causes the gyroscope temporarily to step over by some unknown amount, and can you process this effectively and get it all out? And the answer is yes, you can, but of course it complicates the data, though in some ways less than you might naively imagine. So have I answered your question or not?
We'll take one more question. Up there? Okay.
Was the coating uniform? They're coated with niobium. They were sputtered. How did we get them uniform? Dale Gill may be here. Are you here, Dale? No. He devised the method of coating, and it consists in the following, that an icosahedron has 20 corners and 12 faces, and so that's 32 uniformly distributed points. And so we coated the sphere from 32 different directions with a manipulating device to rotate it from one position to the next. And actually, Dale discovered that sometimes when you do that, there's a certain loss of register, and it's actually best at a certain point to invert it through 180 degrees and do another 32 coatings, and eventually got very, very uniform coatings. That took quite a number of years to figure out how to do. And part of the trick and the problem was to also make sure that you're doing all of this and still have superconducting coatings, because some of the ways we tried destroyed the superconductivity. along the direction, we have 4 gyros in a straight line, or are you worrying about how well they're aligned sideways? They're aligned sideways to about 4/1000ths of an inch on a straight line, and that was quite a feat of assembly to get that to go right. That's one of the reasons why we don't roll the spacecraft much faster than 1 minute roll period, because you put centrifugal accelerations on them about that. Along the direction, of course, there is only one gyroscope that you can make drag-free at any one time. But then you get accelerations that are parallel to, because you have the spin axis lined with the star, the acceleration is parallel to the spin axis and therefore doesn't cause significant torques. Of course, it's not quite parallel because the spin axis is misaligned by a small amount. But when you put the numbers in, you're down effective cross-track accelerations of 10 to the minus 12 average, 10 to the minus 11 average. Is that sufficient answer?
Very quickly, did you levitate the sphere while you were sputter coating it?
Did I never what?
Did you levitate the sphere while you were sputter coating it?
No, it sat on a manipulating device which could be rotated in 2 axes within the sputtering system.
You had a point in Nancy. Congratulations, I spent many years sputtering.
Well, it didn't take all that long to sputter, but at one point we tried levitating it on argon, which is very nice, except that it now is no longer superconducting.
Well, let us thank Professor Everitt again. I must say that I'm most pleased to hear that there will be a talk on STEP in 6 years, which is within my lifetime. In the interim, we will have a program this summer. You should watch for it, right, Pat? And we will resume Brainstorm in the fall. Do look for it and join us again. Good night.